Good afternoon, everyone. Today I'm going to speak about this turbulence in a stable background studied at particle levels. So this is a fluid problem that is being studied not using any fluid model, but using at particle levels with first principle approximation using Newton's equations. This is the outline of my talk, and so turbulence is omnipresent in our nature. Flowing rivers, and then the solar surface is highly turbulent, and then in canals and behind the jets, and also in rain droplets are also formed due to turbulent phenomenon. So turbulence is omnipresent in our day-to-day life. So it's very important to understand the turbulent behavior. So there are two types of turbulence. There are two types of turbulence. One is supercritical turbulence and one is the subcritical turbulence. So we all know very well about the supercritical turbulence. The Kolmogorov 1941 theory is based on the supercritical turbulence. But when we talk about the subcritical turbulence, then it deviates from what we usually know and what we usually do at ICTS. And first thing is the universality. When you talk about this Kolmogorov theory, then this turbulence is independent of the initial perturbation, strength of the initial perturbation or the type of the initial perturbation. Also, it is independent of the aspect ratio that is used to study the system. But when you consider about subcritical turbulence, the behavior varies and universality is no more there. And also, in case of a supercritical turbulence, an infinitesimal perturbation is able to make the transition to turbulence. But in case of a subcritical turbulence, you need to have a finite amplitude perturbation. And we have homogeneity and isotropy in case of a supercritical turbulence. But in case of subcritical turbulence, we have the formation of the spots of slugs, bands. These are some kind of patterns that is formed in a laminar background. Because of this, this homogeneity isotropy is also broken in case of a subcritical turbulence. And we know all about the cascade of energy from large scale to smaller scales. So there is no clear sign of the cascades in case of a subcritical turbulence. And the energy distributes through this self-sustaining process, means with streamwise vortex gives energy to streamwise velocities. And again, this streamwise velocities gives energy to this streamwise vortex. And through viscosity, this energy is dissipated at the smaller scales. So, and also there is no clear 5/3 power law for this subcritical turbulence. And this is one of the most important feature of subcritical turbulence is that the laminar and turbulent region coexist together, which we'll explain in the upcoming slides. So there are several flows like plane quade flow, plane pipe Poiseuille flow, or a counter-rotating tail of quade flow. Out of which I'll choose plane quade flow to explain subcritical turbulence at particle levels because of its simplicity. I will explain what the profile of plane quade flow is. And first, Romanov shows that as it is subcritical turbulence, this flow is highly stable. Means even if you apply some infinitesimal perturbation in between Reynolds number 0 and infinity, this will the perturbation will eventually die down, and you have stability in your system. So it will never become unstable even Reynolds number is in infinity. But and again, then Davy used Orr-Sommerfeld equations, and he showed using this differential equations, and showed that you can solve these equations using asymptotic expansion, and you get some eigenvalues which are complex in nature. And of course, we have stability in the system, though imaginary part of the eigenvalue is always less than 0. But when you have this case, and when your wave number scales as r to the power half, and then in some cases, when your Reynolds number is very, very high, then your this eigenvalue is very small, means it's very nearby 0, asymptotically is becoming 0, and it is going negative minus Ci. So it gives a hint that asymptotically one can reach instability that is can be seen from this Orr-Sommerfeld treatment of Davy in 1972. But ultimately, even if you have infinitesimal perturbation, a plane quade flow is never going to get unstable, or there is no transition to turbulence. And then we have this phase space diagram like this. As you see that have told earlier that the universality is lost in case of a subcritical turbulence. So this behavior changes. This is the Reynolds number. This axis shows the Reynolds number, and this is shows axis shows is the aspect ratio of the system. MFU is the minimal flow unit, and you can see that Reynolds number 325, you had the onset of pattern formation at this aspect ratio, and in between 325 and 410, you can see the formation of patterns. But as you go beyond 410, and this uniform turbulence region begins, but this is not very well understood. But so the critical Reynolds number for plane wave flow was found to be 325. And it is found using the DNS of Navier-Stokes equation. And when this kind of pattern formation occurred, so there is a coexistence of laminar and turbulent region. These black regions are really laminar, and these bands, white bands, are this turbulent regions. And whenever this regions, this pattern formation occurred, he used to get this critical Reynolds number for every case in this diagram. A similar treatment was done by this author Liang Xi et al. And this author found that this calculated this splitting rate, means one stripe splits and becomes two. That is the generation rate, and the decay rate similarly they can calculate, and this plotted as a function of Reynolds number. There is a crossover at 325. So both results show just the 325 is the critical Reynolds number for plane wave flow at this aspect ratio. So, but if you have different aspect ratio, then you have different critical Reynolds number. So you can, this is the kind of plane wave flow that I'm talking about. And I can show you an example in which, let's press no. I don't know to show the movie. Go ahead. So, so earlier, so there are two profiles here that I am showing. One is the simple piecewise linear profile, and one is a plane wave flow profile. And just apply a small amplitude perturbation, and you can see that you can see some random fluctuations in case of a plane wave flow, and you can see this already. You can see some formation of this unstable vortices. So when you apply a very small amplitude perturbation, in those cases, this has already become unstable, and this some random fluctuations are being observed, but this is still stable. So that's why you can say that this supercritical turbulence can be represented by this diagram, where you have a ball in unstable configuration. When you put a very small impedance perturbation, in case of supercritical turbulence, just it will become unstable, and the subcritical turbulence can be explained by this configuration, when you so that you need to apply a very high amplitude perturbation in order to have some turbulent behavior. And just 3 minutes left. So I have not done this problem in using fluid models, just using this kind of medium. Where in the plasma, you just put some dust particles. And why it is the stable background? Because the dust particles, they have reaction frequency around hertz, 10 hertz to 50 hertz. But in the background, these electrons and ions have reaction frequency around kilohertz and megahertz. That's why the background is stable. What you do in one of my projects is put particle in a turbulent medium, but it is different from that. We put these particles in a uniform background, and these particles are electrostatically negatively charged, and this is just the electrostatic fluid. And why I have chosen this fluid is that the reason is that when you have a some fluid, say 1 mole of fluid will have 10 to the power 23 number of particles, but here even lesser than around 1 million, like 0.7 to 1 million particle will give good statistics, and more of the instabilities and turbulence related studies can be studied using this medium. So this is the electrostatic medium, but non-magnetized, but most of the fluid studies can be performed. I'm skipping these slides. So this is the simulation domain that I'm using. So this is the potential through which this particles interact, and this is the kappa, the length scale of the interactions. The higher the value of kappa, the smaller the range of interactions. So quickly go through. This is the how the averaging is been done, and this is simple Newton equations. They are simply interacting with this Newton's equations, and this is this so how why the amplitude of perturbation is important. So this is how it differs from supercritical turbulence. Means when you have a smaller amplitude, then you don't have any kind of spot formation. But as you increase the perturbation strength, then you have this spot formation, and this you don't see any self-similarity here. And this is a driven dissipative system. That's why the Reynolds number and viscosity will change with time. In Navier-Stokes, we can keep the Reynolds number fixed, but here we cannot. It will change with time. And some of the results, like when you change the range of interaction, the behavior also changes. You for some kind of range of interaction, when kappa is 4, then you have this kind of turbulence spot. Is called butterfly-like structures. But when you have when you change the range of interactions, then you have this small scale alternative small scale structure is formed and surrounded by large scale flow, and it's also evident from the scale weighted power spectrum. You can see this small scale structure corresponds to this peak, and this surrounding large scale flow corresponds to this peak. And you can see that later this the oscillations between these two dominant modes also reduces as I increase the resolution of the system. And quickly go through this is the this quadrupolar flow when you average over y. So this turbulence, just 1 minute. Okay, so this has a good matching with the fluid simulation results, and this also shows that as you increase the system size, and then this also shows this for subcritical turbulence. It depends upon the aspect ratio. It is not a universal behavior. So you can see that these the oscillations between these two dominant modes has reduced, and also the dominant mode has shifted a bit here, and also there is a good matching with the experimental results. And this is the, yeah, and also the, localization is been observed here. As in the supercritical turbulence, you can see that these two vortex bands broken into, and they are merging with each other. But in case of a subcritical turbulence, you can see localization. These bands are stationary because the stable the background flow is very stable, and these bands cannot go beyond a certain threshold length scale. And this is some of the newer results, and I have shown that when you change the type of perturbation, earlier I was using some kind of counter-rotating velocity fields, velocity structure to perturb the system. Now when I use a columnar vortex, then there is a difference in between this turbulence structure. So yeah, so subcritical turbulence is not universal. This is what has been seen when we have different type of perturbation. And for stratified system, we have the quadrupolar. This monopolar structure has broken down into quadrupolar structure, and for unstratified, it is broken down into tripolar structure, which is something new that we have observed. So that's the conclusion. So this we have seen that subcritical turbulence behavior is not universal. That has been observed using this particle level simulations, and we see the coexistence of laminar and turbulent region. So L is missing here. Sorry for this typo. And this finite implicit perturbation. Only a finite implicit perturbation triggers a transition to turbulence. And the sport growth and the dynamics has been studied. Well, Reynolds number is keep on varying as a function of time, and also with the experiment we see some excellent agreement. So thanks a lot for your attention.
We have time for a few quick questions. So do we have any questions?
Hi, Suruj,
Yes.
the potential do you use, does it ensure no collision, or do you still have collision in your
The
particles?
potential that is used, this is for point particles, and this ensure I think there is no collision. For collision, you have to put a term extra, minus nu into Vt. Okay. This doesn't ensure any collision. Even if you take hard particles, this also ensure that there is no collision and it will simply evolve in time.
And if you change the potential, does the system dramatically change, or?
If I change the potential,
Yeah.
since I have not used the other potential because I want to study in this medium. But if you use say a linear dot potential or some kind of potential like it is level of lesser potential, it becomes some sign. It becomes the depends on the orientation. Uh, the behavior you'll see this for this potential. We see that the Reynolds number is keep on varying. But if you use Leonard potential, we believe that this Reynolds number will remain fixed. But here, using this potential, we cannot fix the Reynolds number. That's the disadvantage we get from here. But yeah, if you change the potential, the dynamics definitely will change.
Thank you.
Yeah.
Yeah. So I was wondering these particular turbulence spots you're talking about.
Yeah.
Do you have any idea how their size changes with various parameters? Like, is there some scaling?
How the size of the simulation box?
Size of the turbulence spot.
How the size changes?
Yeah. Like what fixes it? Like how does it depend on, let's say, the strength of the perturbation or something? Or
Yeah, size of the system.
not the size of the spot, I'm saying.
Okay.
It is size of the spot.
Yeah, it's much more dependent upon your strength of your perturbations.
But how does it depend? Is it like some power law or is it something complicated?
Yeah, the size means it expands up to some limit. Say there is no power law for it. I don't know if there is any power law, but as you increase the strength of perturbation, and also it depends upon the system size also, and how long it will evolve, that also depends, and also the viscosity that you use, that also depends. But there is no power law that till I know about it, but we can think about it.
But you're saying it depends on the full system size and probably the aspect ratio.
Yes.
Okay.
Yeah.
I have a small question. Why this is like not universal? Like, what's different between this and like homogeneous isotopes?
That's a good question. So this is what I was thinking about. So in case of a supercritical turbulence, so Kolmogorov theory says that your whatever initial condition you use, or whatever perturbation or whatever perturbation type you use, every in the inertial range you get self similarity, right? If you zoom into the system, everything the structure are similar. But here there is no inertial scale, inertial length scale, and there is no cascade here. So that you can say that from large scale to small scale there is an energy transfer. This is something like coexistence of laminar and turbulent regions that is being generated when we apply very high amplitude perturbations. And as these structures are produced, and there is no inertial range here, that self similarity is gone. And from that perspective, I think you don't have the universality in this case. As you change the aspect ratio, it will say you change the initial conditions of perturbation, it will change. If you change the strength of the perturbation, it will change. So in case of a plane quade flow or pipe Moisely flow or counter rotating tailor quade flow, I don't think you will get any kind of universality. But people have found in percolation transition some universality, but that I don't know very well.
Is it because of the boundaries? Are there boundaries that stops making itself similar, or it's?
No. The boundaries have no any kind of contribution to it.
Okay. Thanks.
I think it is the kind of flow itself it makes this.
Okay, we'll just take one last question.
So you said you compared like the molecular dynamics simulations with the hydrodynamics, right?
Hydrodynamic results. Yeah.
Yeah, so
Yes.
for that, I mean, like, for that, you need the transport coefficients like the viscosity and thermal. So how did you get those? I mean, from the,
This transport coefficients, one can, so I have just compared these structures, but viscosities and all these quantities can be calculated using this green cubo formulations.
that's what you did, is it? You
I have done, but these results has not been put, but you can calculate it using green cubo relation also. And I have used some references in which he already calculated for different kappa values. I have picked up those values and compared with that. But here, exact comparison is not possible because the Reynolds number is changing at every time. So in hydrodynamics, most of the cases Reynolds number is fixed. Most of the Newtonian fluids, but non-Newtonian fluid may I have not compared with non-Newtonian fluid, but yeah, but this comparison is almost similar. And one more, this conclusion is that even it's an electrostatic fluid, for higher range of interactions, it's behaving like a neutral hydrodynamic fluid. Yeah, that's why this, although this Reynolds number is changing, and in this case, the Reynolds number is fixed.
Okay, thank you, Suruj.